Today we're going to talk about mixture of experts. My goal with this video is to explain MOE to you as simply and as quickly as possible. So in a short amount of time, I want you to develop a fundamental understanding of how MOE works, which means we're going to start conceptually. I'm going to sketch out the basic idea, explain the architecture, what is happening and why do we do it. And then I want to move right into the coding example. We're going to implement an MOE example in PyTorch because the moment you have to put your understanding into code, you really see what you do understand and what you don't understand. So that's the best way, in my opinion, to learn stuff. Now, we're not going to focus on building something useful in this video today. We're not going to work with real data sets, and we're also not going to build a transformer-based architecture. This is really just going to be a proof of concept so you understand how mixture of experts work. So we're going to build it from the ground up using PyTorch. Now, if you like this video and if you get value out of it, let me know by hitting a like button and subscribing. And now let us get right into it. Alright, so we're going to learn about mixture of experts in this video today, written like this: mixture of experts, and abbreviated MOE with a lowercase o. Now, as the name already says, we're going to have multiple experts and we're going to mix them in some way. But what I want to do now first is I want to explain conceptually the idea of MOE. How does it work? What is the idea behind it? Why do we even do that? And then I want to go into PyTorch and build an example, a proof of concept using mixture of experts from scratch. Now, most of you guys have heard about MOE before already because this is a thing commonly used in architectures nowadays, in large language models architectures to be precise. So whenever a new open model is released, you will hear something like it uses latent MOE or stable latent MOE or some variation of that, something related to MOE, mixture of experts. So what I want to do now is I want to copy and paste an image here of the very well-known transformer architecture. I'm not going to cover the transformer architecture today. This is going to expect you to at least know to some degree what is happening here. Stuff is coming in, stuff is coming out. And in between here, we have a feed-forward layer. This is basically just a neural network, a feed-forward neural network. And the idea is quite simple. We pass token representations into this feed-forward neural network, and we then pass the output on to the next layer. Now, of course, in practice, all of this happens in batches, so we don't do this token by token. But for the sake of simplicity, we can zoom into this process now on a token by token basis. Let's say our token has a dimensionality, an embedding dimensionality of 128. So we would have 128 numbers here representing an individual token, which means we also have 128 neurons that we have to connect to here in the first layer. And then usually we go broader. So we have, let's say, something like 512 neurons here. These are just example values, and all of these, of course, are interconnected. I'm not going to draw this now in the most beautiful way, but imagine all these neurons being connected, and maybe we have a second layer. This can differ from architecture to architecture. We might have 512 here again, and then in the end, we go back to our token dimensionality, which is 128. So this whole thing here is the intelligent processing of the token. All of this, of course, interconnected here. I'm not going to draw all of this, but that is the feed-forward neural network here in this transformer architecture. So this is an intelligent process, if you train it properly, that does stuff. So token representation comes in, intelligent processing happens, and then the output is fed to the next step. This is how we do it in ordinary transformer architectures. Now, with mixture of experts, we have multiple of these networks and we call them experts. So I can just put something around here and refer to this as expert 1. And then I can say I want to have the exact same architecture with different weights, of course, but I want to have the exact same thing and call it expert 2. And I can do that n times, and then I have n experts. So expert n. Unfortunately, I don't have a copy paste feature here, so I'm just going to write copy and paste. It's basically the same idea, of course, with different weights, because different training is going to happen or different signals are going to go through the individual neurons, but the architecture is the same. We have multiple experts, and how we deal with that now is we define how many experts we want to have. Let's say I want to have E1, E2, E3, and E4. And what I do now is I define, first of all, the number of experts for my model. So this is a architecture choice. How many experts do I want to have? And also, how many of them do I want to activate? Let's say I only want to activate the top 2 experts for a given token. And who decides which experts I'm going to use is something called a router. The router gets the token in, so we don't feed the token directly into an expert like we do it here with the feed-forward neural network. We feed the token into the router. And the router then produces two things. On the one hand, it produces the two experts that we're going to consult. For example, 1 and 3 would mean index 1, index 3. So actually this one here and this one. And then it also tells me the weights. So it tells me, for example, that the decision or the output of expert at position 1, so expert 2 here, has an importance of 0.3. And then the other one has to add up to 1, so 0.7. 70% of the answer is going to come from E4, and 30% of the answer is going to come from E2. And once I have that, I take the token and I route it into E2 and into E4. So this is then the experts. These are the two experts that I choose to use. Then they produce some result. Let's call it output 1 or out 1 and out 2. And what happens then is they're combined. The combination is basically, I say output is equal to out 1 times 0.3 plus out 2 times 0.7. That is the basic idea. This produces then the output of this mixture of experts layer. That is as simple as it gets, not the most mathematical or technical explanation. The only difference is we don't have one feed-forward neural network that we always pass everything through. What we do instead is we pass it to a router. The router tells us which of the experts to use. And of course, we can have 128 experts and we want to use 64 of them. That's also fine. You can also use 4 of them. You can use almost all of them. It's up to you how you design your architecture. Every MOE model is going to make different design decisions, but the basic principle is you have a router. The router tells you which of these to use and also the importance of their outputs. Then you feed the tokens through those experts, and then you get your outputs, you combine them, and you proceed. So this arrow here after the combination is the same arrow as here. You just put it to the next layer. And of course, there are many different things that we can do here. Additionally, we have, for example, latent MOE, where we actually reduce the dimensionality of the tokens before we route them through the experts, but we don't do that for the router. This is what Kimi does. Also, Kimi, for example, has shared experts. These would be special experts. Let's call them SE1 and SE2. These would always be used. So these would always get the tokens and contribute to the output. But this is then depending on the architecture, depending on the specific type. We don't want to overcomplicate things, so we're going to keep it simple and focus only on the raw mixture of experts, the fundamental one. And of course, one thing that's very important before we move on with the PyTorch implementation, why do we even do that? What's the benefit of using mixture of experts? The number one reason to use it is to reduce compute. So the idea is if I want to process a token, I don't have to activate all the weights in my network. I can only activate specific weights which are very well suited for this specific task, which is the token at hand. And by doing this, I save compute. I don't save VRAM because I still need to have all the weights in memory, but I do save compute, and it's just faster to train and to process, or faster to train and to do inference. All right, so I think we sketched enough. Let us go into implementation mode. For this, I'm going to navigate to my tutorial directory, and I'm going to create a new UV project with PyTorch installed. So I'm going to say UV add torch. Feel free to install PyTorch however you want. Feel free to use whatever development environment you want. The important thing is the code. Whether you write it in VS Code, in JupyterLab, or in NeoVim doesn't really matter. Now, in my case, I'm going to write it in NeoVim. So I'm going to open the main PY file. We're going to start from scratch here. In terms of beginner friendliness and level of complexity, I will explain every single line of code. I will explain what we're doing here. This is the purpose of learning, but I'm not going to consider this a PyTorch crash course for beginners. I already have this on my channel. So if you don't know anything about PyTorch, if you don't understand neural networks at all, this video might not be the best video for you. You should know at least the basics, but I'm going to, of course, explain everything here from scratch. So let us start with the imports. We're going to, of course, import torch. We're going to also import torch.nn as nn, and we're going to import torch.nn.functional as f. These are the usual aliases. And we're going to start by defining now a class called expert. Obviously, this is going to be one expert, and then we're going to use this class in a mixture of experts model. So that's going to inherit from NN module. And in here, we can create a constructor in a init method, which takes in self. It takes in the hidden dimension. It takes in the expert dimension. Then we call the super constructor of the parent class like this. And then we can just define the network. So self.net is going to be nn.sequential. And in here, we just want to have a simple linear layer. So we're going to start by saying nn linear, mapping from the embedding dimension to our expert dimension. So linear from hidden dimension to expert dimension. Then we want to have an activation layer, so a GALU, if that's how we pronounce it, Gaussian error linear unit. And then we want to have another linear layer which maps back the dimensions. So from expert dimension to hidden dimension. This is exactly what we also discussed in our sketch here. Remember, we get the token representation in and we feed it through the network, which is larger in this case, 512 from 128. We process it and then we get it back to 128. So the hidden dimension would be our 128. Then we have 512, activation, 512 again, and then 128. That is the idea. Now we just need to implement our forward pass. So forward here is going to take self and x as input. And the only thing we need to do is we need to return self.net applied onto input x. This is our expert. So this is of course only a subnetwork in the overall architecture. The overall architecture will be a second class, which we're going to call sparse MOE. Sparse because we have a sparse activation pattern. We don't use all the experts for every token. This is also going to inherit from NN module, and the init method is going to take as parameters self, hidden dimension, expert dimension, then also the number of experts that we want to use. Let's say the default here is going to be 4, and also how many of these experts we want to activate for every token. So top k is going to be equal to, let's say, 2 by default, but of course we can always adjust that. Then we can just say self, or actually first of all call the super constructor, so super and then init. Then we can say self dot number of experts is equal to number of experts, and then also self.top k is going to be equal to top k. But most importantly, what we do in the constructor is we define our router and our multiple experts. So for this, we're going to say self.router, and that is just going to be a single linear layer which takes in a token, so hidden dimension, and produces number of experts logits. So for every expert, we get a logit, and then we use the softmax function to determine which k experts we actually want to use. That is what the router is going to do. And the experts are just going to be a module list. So self experts are going to be equal to nn module list. And in here, we're going to have a list comprehension expert with hidden dimension and expert dimension for underscore in range num experts. But all the interesting stuff and all the complicated stuff actually happens in the forward pass. So let us define the forward method here, which takes self and x as input. And the first thing I want to do is I want to get the input into the right format. So I'm going to say x.shape is what I'm looking at. And this is going to unpack into 3 values: batch, so the batch dimensionality, the sequence dimensionality, and the hidden dimensionality. And what I actually want to do is I want to get my input. I want to store this as tokens. I want to get my input and reshape it in the following way: -1 and hidden. So what does this actually mean? If this returns that the batch dimensionality is 4, so I have 4 examples, the sequence length is 32, and the hidden dimensionality is 128, so that is the token dimensionality. If that is the case here, what this is going to do is it's going to pin the token dimensionality, 128, and it's going to multiply the other 2. So in this case, it would also be 128, but if this, for example, is 5 and 30, this would end up being 150. So the idea is I have 150 times or 150 tokens, and those tokens have this dimensionality. So we're just getting the tokens in a different format. These tokens now have to be fed through the router so we know which experts to consult. So for that, I'm going to say router underscore logits is going to be equal to router being applied to tokens. And actually for this to work, of course, I need to say self.router. And the logits now are just the raw output values. I need to get the probability. So I'm going to say router props is going to be equal to f.softmax router logits and dimension equals to -1, which basically means applied to the last dimension. Now from these router probabilities, I want to get the top k results. I want to get the top k experts to consult. I want to get the indices, so which experts to consult, and also the probability so I can calculate the weights. So I'm going to say here top underscore probabilities and also top underscore indices is going to be equal to torch.topk router props self.topk and dimension -1 again. Now the problem is that to get the weights, I want the weights to also add up to 1. So I need to renormalize them again, which means I'm going to take the top probabilities and I'm going to say that these are the top probabilities divided by the top probabilities dot sum. Dimension is going to be -1 again. Keep dimension is going to be true. And important, to avoid divisions by 0, I'm going to say clamp minimum, and we're going to use something like 1e minus 9. So a very small number to just not have divisions by 0. This normalizes the probabilities, because otherwise here I'm getting the probabilities overall, and now I want to have the weights or the probabilities within this group. I want it normalized so all of them add up to 1. Then we're going to prepare an output tensor full of zeros. So output is going to be equal to torch zeros like, and we're going to pass tokens here because they're going to have the same, or this output tensor is going to have the same shape as the tokens tensor. That is the goal here. We get tokens in, we produce tokens for the next layer, the next step. And now for this batch that we're currently processing, we want to iterate over all the experts and assign the tokens to the experts. So I'm going to say here for expert ID and expert in enumerate self.experts. What I want to get here is the indices of all the tokens that are assigned for this or to this specific expert. And I also want to know which rank this expert has, so how important this expert is. So what I'm going to say is I'm going to say token indices and slot indices is going to be equal to torch.where, and then the top indices, which we calculated up here, they have to match the expert ID, or the expert index in this case. Now, if not a single token is relevant for this expert, we want to just continue. So I'm going to say if token indices num_l is 0, or let's say less than or equal to 0, or actually equality is enough here, we can just say continue. And otherwise, I want to get the tokens that are relevant for this expert and I want to process them. So I'm going to say expert tokens is going to be tokens, and I'm interested in the token indices that have to be processed by this expert. And then very simple, expert output is going to be whatever happens when we take this expert and we feed the tokens through that expert. So the expert tokens have to be processed by the expert. That is going to give us the expert output. And then for the weights, we just need to consult the top probabilities here. So weights are going to be equal to top probabilities. First of all, the token index, and then also the slot index. I need to know for this specific token, which position do I need to look into to get my weight. That is that. And then we're going to do an unsqueeze -1. This is just so the dimensionality is all right. And then we're going to say output index at, very important, you want to use the underscore because that's going to do it in place. So we don't have to reassign it. Index at, and we're going to do this in the 0 dimension, the row dimension. The indices we want to target are the token indices, and there we want to add whatever happens when we take the expert output and multiply it with the weights. So this is the contribution of our expert right now to the overall output. The output is outside of the for loop, and it's the result of the K experts adding their stuff to the output. Now, this would already be enough when it comes to implementing mixture of experts, but I would like to also add a load balance loss. So a loss that penalizes unbalanced behavior when it comes to routing, because I don't want the router to pick 1 or 2 favorite experts and always route everything to them. I also don't want the router to pick 2 experts, but effectively only use 1 because it assigns almost 100% probability to the first one and no probability or no weight to the second one. That should be penalized, and we're going to do that by first of all saying mean router props, or mean router prop, I should say. And here we're going to get now the average probability, the average weight for the routers. So router probabilities mean, and the dimension here is going to be 0. In addition to that, I don't just want to focus on the weights. I also want to know how often are you selected in the first place. So I'm going to say here selected fraction is equal to, and for this we're going to do a 1 hot encoding. So f1 hot top indices, and number of classes is going to be self.number of experts, obviously. So that's going to do a 1 hot encoding. I want to then turn this into float, and I then want to also get the mean with dimensions. Here is going to be a tuple 0 and 1. And then finally, we can define the load balance loss to be equal to self.number of experts times torch.sum, and then the mean router probability times the selected fraction. Why is this reasonable? Think about it. Let's say we have 4 routers and top k is equal to 2, or k is equal to 2, I should say. What happens if I have everything completely balanced? So I get 0.25, 0.25, 0.25, 0.25 for the averages everywhere, and I get that for both lists. So for the selected fraction and also for the mean router probability. And we're doing torch sum here, so that would be 4 times 0.25 and then times 0.25, which would basically just be 0.25, but then the whole thing times 4, that would be 1. Whereas the calculation, if I have completely unbalanced averages, so let's say I have 0, 1, 0, 0 for both lists, then the calculation would all of a sudden be 4 times 0 plus 1 plus 0 plus 0, and that would result in 4. So we get a higher loss if we have unbalanced weights and also unbalanced selection fractions. This is the idea of the load balance loss, to just prevent this. So finally, we can then say return output.reshape into the same form as before, which is batch, sequence, and hidden. So this is, remember at the beginning here, what we reshaped. We want to shape it back, and we want to return the load balance loss as well. That is the implementation. Now to actually use this, I'm going to copy paste the code because now we're not learning really anymore. So here I have some sample code, very simple. Again, we're not solving really any useful problems here, but we have MOE, sparse MOE. We define hidden dimension 128, expert dimension 512, 8 experts, top 2 are chosen. We have an atom optimizer, and we train on a trivial task. We get some random numbers from -20 to 20, and we just make this model learn how to take the number times 2. That's the basic idea. We train this, and then I can just enter my own number. The interesting thing here is I also take a look at which expert was selected and what the weight was. That's actually the most interesting part. So for that, I'm going to say UV run main py now. The training happens silently behind the scenes. And now if I type something like 20, probably it's not going to be a correct result, but it's quite close to 40. You can see selected experts 3 and 2 with these weights. Then I can try the same thing again. It's going to train every time I run this now. Not very efficient, I know. But now I can type something like this maybe, or maybe let's go with something that's a bit smaller. And it still gets a pretty decent result considering that this is not part of the training set. Now it used only, effectively it only used the first expert because it assigned a weight of 0 to the second one. So that's not good. We should penalize this even more. So let's now finally go with something like this. And again, it uses only 1 expert. So that's not very good. But yeah, you get the idea. This is how you implement mixture of experts from scratch in PyTorch. I hope you understood how it works. We have the individual experts here. We have multiple of those. We have a router which chooses the experts that we want to use, and then we just route the tokens through those experts. We aggregate the results or we combine the results by adding them together and considering the weights, and then we just produce the output. But of course, this would be part of a transformer architecture usually, not just a standalone thing. So that's it for this video today. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, in case you're interested, on my website, you will find a services tab and a tutoring tab. There you can contact me if you need help with a project, if you need a freelancer, if you need a consultant. You can find a link to contact me via email or LinkedIn at the bottom of both pages. Besides that, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.